All right, cool. So I'll just start. So good morning, everyone. I'm Joshua. I'm a grad student at the University of Illinois. So I've been very lucky to have a chance to collaborate with lots of people right here, like Jion and Simon and Phil. So that's why I'm here to talk about some of the stuff that I found really interesting. So today I'm going to talk about a paper that is recently put in on arXiv um, by Katie Bouman and He Sun from Caltech. And the title is called Probabilistic Imaging. So uncertainty quantifications and multi-module solution characterizing computational imaging. I know it sounds really tricky, but I'll explain what is going on in a few minutes. Okay. So I know there are a bunch of new people right here. So I thought about, and I'm also maybe only a few of the example that are not in Stanford/FLAC people right here. So I thought about taking a few minutes to introduce myself. So I'm a physics PhD student at University of Illinois. So I mainly work with, I'm in physics department, so mainly work with physicists and astronomers. So I've been working with Gil Holder, Charles Gammy, and Xin Liu on a lot of broad topics, mainly on machine learning applications in astrophysics. So I'm also a member of the Event Horizon Telescope starting this year. Yeah. So some of my interests are like dark matter and strong lensing, supermassive black hole, especially, and also machine learning, especially reinforcement learning these days. All right, so today's story is about a black hole image. So the story begins with last year, the Event Horizon Telescope collaboration announced we have first image of a supermassive black hole, M87. So as a physicist point of view, what we like to understand is like what kind of physics can we learn from this black hole image? And just to give you an idea about how how did people do observations on top of these black holes? So just to give you an idea of how big this black hole is that if you can put a whole solar system in this black hole, and the black hole is like a 10 to 9, roughly 10 to 9 solar mass. So I think the event horizon size is actually pretty big. But because of the distance that you're actually taking into account, so actually the actual angular size of this black hole is super small. It's like 40 micro arc seconds. And if you are familiar with strong lensing, like one of the famous example in strong lensing is that you have STB81, which have a diameter roughly like 2 arc seconds. So like there's more than 10, well, roughly 5,000th time difference in the angular size. So in order to take the image of the black holes, what we need to do is to have a right wavelength that you can try to avoid some interstellar electron scatterings. And people found the right wavelength, and in order to match so basically, in order to resolve the size of the image of the black holes, people figure out that you need to have Earth-sized telescopes. And by Earth-sized telescopes, what I mean is that naively, we couldn't build a telescope that fully covered Earth. Otherwise, we wouldn't be able to see the sunlight, beautiful sunlight, especially have a lot of in California. But I think what people end up doing is that people use a lot of radio telescopes around the globe to try to collect the data from this black hole emission at the same time, so that they are sort of using it as a network, which is what we call the Event Horizon Telescope. So it's actually composed of multiple radio telescopes around the globe. So the idea of how this radio telescope, because I'm not going to jump into detail, but just to give you a broad idea, is that you have some signal on top of the sky and the light is coming to the observer. And because of the light is traveling at the speed of light, so some of the signal arrives part of the antenna first, and some of them will arrive later. So there will be a phase difference. basically you can have multiple antennas to measure basically the inference pattern of it. So that's why this is called the radio interferometry. But due to the technical complexity, I'm not going to talk about detail, but this is basically how the event horizon telescopes work. And I'm going to focus on more on probabilistic imaging part of it later. So far, is there any questions?
Are you going to explain how the knowing this? So I'm really don't know much about radio astronomy. How knowing the small phase difference from the small distance, the change in distance traveled, how that's useful for imaging?
Yeah. So basically, you can imagine that you're basically doing a bunch of like, well you're actually measuring the phase difference from a single source, but there could be multiple sources on top of the sky. So basically, what you are sort of doing with this radio telescope is you're sort of like doing some convolution, but with uneven sampling. So what your data is going to end up at is that you're going to end up at, with some sparsely sample Fourier space data. So imagine, which is what I'm going to talk about right now.
Oh, I see. So it helps you knowing what the delta t should be. It helps you separate signals in the. Got it.
Right. Yeah.
Thanks.
Yeah. So basically, the idea is that basically you use a lot of these antenna to record the signal, and the raw signal is actually made of voltage and the time. So I think measuring delta t is extremely important for event horizon telescopes. So I think people use atomic clocks to very high precisions when they're doing this task. But I'm not involved in any instrumentation part of that, so I didn't know all the details. But the idea is that you're going to end up having some data that are living in the Fourier space because of the convolution. So when we talk about the famous black hole image, what I'm showing right here is actually what the raw data, well, the process data looks like. So on the left-hand side is something we call the UV coverage. If you're familiar with radio interferometry, is that basically this is all the color dots are represent from data collected from pairs of telescopes. So basically you're only sampling data in this Fourier domain right here. So your XY coordinate are, you can imagine it's like a KX and KY in the Fourier space. And due to the limitation of the telescope, you're going to sparsely sample of it. And on the right-hand side is the plot we call the visibility amplitude. So basically, the idea to understand what this plot means is that imagine you're looking at a black hole. So you'll probably see a ring size. And when you can do Fourier transformation on this ring size image, then what you see is actually like a bunch of Basel functions. And then when we talk about visibility amplitudes, is that you're actually taking the absolute value of it. So you basically square it. So the Bayesian function, the negative part would become positive part. So that's why you're sort of seeing the dipping shape that are labeled in green right here. So when people talk about detecting black holes with radio interferometries, is that when you can see this kind of dipping effect, if your data is lying on top of the crescent model, which is labeled in green right here, we think there's a very high chance that this is a black hole. And if it's just a Gaussian blob, you will see the sum of the drop down right here. So this is basically just some background about what the raw data, what the raw data of the black hole image looks like, which is not going to be, I'm not going to talk about any detail of it, but this is just some parameters that we're going to use later on. Right, so basically, the interesting thing is that these two looks very different. So how do you come from this data back to the things that people are familiar with, which is in the image domain, is that people need to build a lot of like computational imaging algorithm by that's took the data from visibility and bring back to the real space. And basically in radioferometries, I think there are mainly two trends. And for a more traditional one, there's an algorithm called clean, which I'm not going to talk about today, but basically have to do with deconvolutions. But on the right-hand side, there are some algorithm that is adopted by two teams in the Event Horizon Telescope called the regularized maximum likelihood, which I will talk about in more details today. But the idea is to show you that you can have an image reconstruction algorithm that could generate the image. And due to the sparsity of the data, there are actually many possible images you can generate from this data. And so this is the reason why we're going to talk about this paper today, is that there's actually a lot of probabilities of this image right here. So is there any questions at this moment? Okay, I'll just keep going. So basically, as I described before, basically there are two image algorithms people used. And these is their comparisons. I plotted out right here. So basically, for regularized maximum likelihood, I think it's something that some of the people right here might be interested. It's a probabilistic modeling of of an image for image reconstructions. And in the paper I'm going to talk about today is an extension of these regularized maximum likelihood method. Like they combine normalizing flow, which is a type of neural network, to make it a deep probabilistic imaging. And for the clean algorithm, which I'm not going to talk about that much today, I would say that it's much more hard-coded stuff. Like there's no well-defined prior knowledge in using these kind of clean algorithm, and usually requires a lot of human expertise and experience on their hyperparameter tunings. So it's really hard to evaluate the uncertainty if you're using directly with clean algorithms. Okay. All right. So so jumping back into this black hole observations. So what we're seeing right here is the UV coverage of the Fourier space. So basically, because we only have a few telescopes around the globe, and there are parts of the Fourier domain that we're not actually sampling. So because we're missing those parts, so actually, in reality, there are infinite numbers of possibilities of the real image could be. And to cleverly select an algorithm to reconstruct the image, I think that's what part of the team are doing. And for the regularized maximum likelihood method, what people are doing is that you have an image, which is a real image, for example, on the sky, and you measure the data with radio telescope, then you can have something, some observable, which we call as Y right here. And the image algorithm is basically trying to come up with different possible image and pass it through a function f, which the function right here is usually represented by something we call EHT-imaging. It's a visibility simulation that takes image from each domain and generate visibilities. Then you can basically compare how likely this, by comparing y and a y hat, you can basically compare how likely this image is corresponding to this observation, which I think some of people might be familiar with the pipeline. And there's also some knowledge needed is the how likely is the prior image distributed. So this is something I'm going to talk about later. But I mean, this plot is basically the spirit of the regularized maximum likelihood method for image reconstructions. Okay, so I'm going to skip this. So one thing to notice is that due to the sparsity of the data, usually the reconstruction image will look similar to the original image, but they could look different in some cases because of you don't have full coverage of the information at all. So I think what the regularized maximum likelihood is doing is that it's basically trying to select the best image given the likelihood of your observables and the image you selected and how likely this image is coming from your prior knowledge. Just to give you an example, like I think in most of the image reconstruction, people usually will assume that your image have some continuous distributions. So yeah, that's basically some of the prior you could put in right there. And by putting that prior, you could actually select some of the best image coming from your prior assumptions. So this is the simulated EHT-imaging reconstructions by the pipeline I described before. And this is how it actually works. So I have some really cool video about, I'm just trying to play with the regularized maximum likelihood, which is actually an open source software online, mainly developed by Andrew Shell at Princeton right now. So basically what you see right here is that on the left-hand side, there's a ground truth image. And these are a bunch of data that are just intermediate process of it. But your algorithm is trying to clean up the image using some fitting function in likelihood and its own priors. And it's trying to find the best possible image that matches your likelihood, your combination of your likelihood and priors right here. So as you can see, after multiple steps, the reconstructed image start looking like the input image. And yeah. So this is basically how regularized maximum likelihood works for computational imaging reconstructions. All right, so I'll probably skip the later part.
It's a short side note in the sense that these techniques, a bit different, but not iteratively, but with a fixed prior in that sense, are in standard use in strong lensing reconstruction of images. So when you do, say, a pixel reconstruction or also with shapelets and so on, these are these effectively regularized and you give some prior, but it's hard to quantify it.
Yeah. I think the spirit is actually the same. Like I think what they put in right here is they put in regularizers.
Yeah.
And yeah, right. But that's I think in the paper they're saying that this is actually flexible, depends on the case that you're using. And for the case of Event Horizon Telescope, I think they claim it as a regularizers.
Yeah, thanks.
Right. Yep. Thank you, Simon. All right. So now this comes the important part of this talk, which is like as an astronomer, people will definitely talk about uncertainties. And for Event Horizon Telescope, because I think the image is very sparsely sampled actually. So there's actually huge uncertainties when talking about image reconstructions. So we all know the famous image that are publicly available these days, but in principle, if I'm given a raw data set, there could be multiple different images that carries different probability that could possibly be what the real M87 looks like. So that's why and if you want to do physics on top of it, I think uncertainties, to understand the uncertainty is actually pretty important. And in the previous paper they published last year, and they actually talk about this uncertainty quantifications using a more traditional method. And the question is like, given the observable, which is the visibilities, what's the distribution of the image looks like? So you have one observable, which is fixed, which is measured by the telescopes. There could be multiple image, and we want to know not only the most likely image, but there could be a distribution of the image right there. So the question is, how can we do that? Basically, by extending the regularized maximum likelihood, if you sort of relax it and not trying to always select the best image, basically you can have a bunch of image that are likely to be the real image, and they carry certain probabilities. And so this is something we call the posterior estimation exploration. By given some condition, you already have an observable how likely this image is. So this could be directly sample using, for example, like traditionally using MCMC method, which I'm not going to talk about in too much detail today. But since we are in the eras of deep learning, so I think lots of people are started exploring whether we could use a neural network, especially a particular form of neural network called normalizing flow, to estimate the posterior distribution of the image. And right now I'm going to start talking about how they try to explore the possibility of it. All right, is there any questions at this moment? Okay, I'll keep going. So I think a few months ago, I talked about some neural network architecture. Gio and I talked about some neural network architecture called normalizing flows. So I'm not going to jump into detail today, but normalizing flow is an invertible and traceable neural network that can bring you from a distribution to another distribution using neural network. And just to give you an idea of how it works, is that you basically can start with some random noise. And as long as you have a target distribution, you can build a neural network that gradually transform the original distribution into your desired distribution. And people usually talk about this as a generative models, but you could also think of like it's actually just a series of transformation on distributions. So I think in this work, they use an architecture called real MVP, which I'm not going to talk about details today. But the idea is that when you try to change a distribution from certain distributions, basically the key point you need right here is to calculate the determinant of this transformation matrix. And what real MVP is, so if you really want to calculate any transformation of a certain matrix, it could be quite computational expensive because you need to calculate the determinant all over the place. But one trick people found is that if you can try to make your matrix more like a triangle or diagonals distributed, then you could save a lot of computational time, because basically you don't need to care about all the zeros right here. So which means you save a lot of time. And in I think real MVP, they use this technique by trying to build up a neural network that can handle this part by something we call the affine coupling layers right here, which I'm also not going to talk about detail today, but just to hand waving, showing that if you're interested, this is something I found really interesting, and you could take a look at it. All right. So the idea is that once you have this, then you can basically transform from whatever Gaussian noise you like and throw it into a neural network, and it could generate an image of your desire. And then in order to train this network properly, usually people provide a bunch of samples of the image as your target. But right here in this work, I think they're actually doing slightly different things. So what they are doing right here is that they're basically using this as a generative model to generate whatever image. And there's and they train this neuron, and basically they transform this image back into visibilities using the EHT-im. And then they actually do chi-square analysis on how likely this image would generate these observables, and including all phase. So phase is something that it lives in Fourier domain. So they're basically calculating phase and amplitude chi-square, and also put in some prior knowledge right here, and try to train this network to optimize that it could fit into this observable well. Right. So basically, they're using these normalizing flow as an efficient posterior exploration tools. Right. So I think so basically what they're doing is that let me skip all of this, but they're just trying to basically generate a bunch of image that could fit to the visibility data using a neural network. And in order to do it, you need to optimize your neural network parameters. So usually people do it with backpropagations. And the objective function is to trying to maximize the generated image that could match the observed visibilities, and also have a high possibilities coming from its prior. But what people found in this work is that with this wasn't working very well. There's actually some additional things that people need is an entropy loss. So I think this entropy loss basically encourage your network to explore different possibilities of the generated image. So it could efficiently sample all possible image right there. So I think this is one of the key point in this work they used. So right here, is there any questions?
Yeah, Joshua, I was trying to understand it seems like they have two priors in this work. So but they know what P of X is that correct? They have a functional form. They
know what P of X is, yes, correct.
So then what is Q of X doing if they already know the prior and they already know the likelihood?
I think Q of X is so I don't know the detail of it. It have to do with the neural network parameters. So basically, I think they're sort of relaxing this prior so that it could explore more possibilities at the early times. I'm not sure whether it have to do something related to the mode collapse within neural network.
Do they retrain Q for every Y?
This part I'm not sure, but I think something they tried is that they try to explore. So basically, you can apply a constant beta to time this entropy loss. So if you set beta equals to 0, then that means you have no entropy loss. And if beta is really big, then you are basically influenced heavily by this entropy loss. So I think when they set beta bigger, they found the neural network could start exploring more possible images. But I think what they found is that when beta is is set to 1 matches the analytic estimation the best.
Yeah, I guess what I'm kind of wondering is if they retrain Q for every Y, then in some sense Q is almost a approximate posterior rather than a prior, because it gets re-estimated. It's like a non-amortized posterior inference.
Mm-hmm.
And I'm just trying to make sense of what Q versus P is, and maybe that's the connection there. I don't know.
Yeah, that's a good point. I actually don't know as well. I'm
not sure if Q is a prior. I think, like Joshua said, it's just an entropy term that prevents mode collapse. So this is just like the distribution over Z that's been transformed into X using the flow.
Right, but that's supposed to be the reconstruction, right? That's supposed to be, sorry, the image prior. It's supposed to be able to generate images prior to the smearing from the likelihood. Right, you're going to use the samples from Q as your estimate of the image to do the downstream inference. So Q should either be a prior, but we kind of already know what the prior is, or I guess it should be a posterior or something else, which I guess I'm just trying to frame it in a probabilistic term that.
Yeah. I'm not sure if this is formally the best. I mean, if this term has any, like a good Bayesian interpretation.
I feel so when I talked to the one of the author, I think my impression is that they found that having this entropy loss terms helps generalize your network better. But I don't know the detail of how the training yet, because I think the code would be public after it's been after the review. So this is just a preprint. So I don't know how it actually worked in detail yet.
Where it comes from is like just like the KL divergence between Q of X and Px given Y, right?
Yeah.
So this loss function is trying to variationally minimize the difference between Qx and Px given Y.
Yeah. Yeah. And I guess I just meant, like, if it's redone for every Y, then whether you actually feed Q the value of Y or not, it's still effectively re-optimized for every Y, and therefore kind of a approximate posterior. So I'll think more about it, but I agree with your points that yeah, there's a certain empirical aspect to it about kind of just learning a sampling distribution with a certain kind of regularization on its entropy. That's also another way to think about it. So, sorry to interrupt. Thanks.
No, this is actually good. Thank you, Michael. And, right. So I think to keep the flow going, I think this is basically what they propose in this paper, and that's pretty much it for what they are, the framework of the probabilistic imaging tools. And obviously there could be certain variables that they discuss in the framework, but I think this is pretty much the variational method they use in this framework. So I think this is also like what we discussed a while ago, like they're basically trying to optimize the KO divergence of your Q and posterior, the true posterior, I would say. Right, so, and I think the bottom one is that the actual loss function they could put in right there. And I think in every time when you train the network, I think your Y is sort of fixed. So you basically need to pick an observable, then your network is trying to optimize a series of distribution of the image that can match this observables. So yeah. So then after this framework, they obviously apply this to a bunch of stuff and see what will happen. So basically, on the left-hand side is that they use it with more the old school, the regularized maximal likelihood without a neural network. And on the right-hand side is the neural network versions, the DPI framework. So one thing they noticed right here is that on top these are the truth image and the blurred truth. So basically, due to the size of the Event Horizon Telescope, there's you couldn't really see all the detailed structure because the baseline are not long enough. So the idea is that if you can have a radio antenna on the moon or somewhere in the space, then you could possibly detect some of the fine scale feature right here. But with the current antenna setup, you can only see the blurred versions of it. So one thing they found interesting is that there are actually two modes that are possible to match the observable Y they provided right here. So one thing you can see is that there's a bright ring on the top right corner, and in some other cases, the bright ring is distributed on the bottom left. So these two images, they are all possible that they found in this framework. And so these are actually two different modes that they could use, both regularized maximal likelihood and DPI to figure out. So when people talk about image reconstruction, I think people only talk about one image, but what they're providing right here is that there's actually different modes that are all possibles right here. And so one thing they did right here is that when they reconstruct the image, then they figure out there are actually two modes of the possible image. So they use a technique called t-SNE, which is a dimensional reduction pipeline. So if you're unfamiliar with t-SNE, it's actually a neural network version of PCA. So it's trying to match the image into a two-dimensional thing. So they figure out the image that the brightest part on the left-hand side is the model 1 labeled right here, and they sort of form into its own cluster. And there's a mode 2 right here. So they basically select these two different modes. And what they do is that they could calculate the mean of all the things in mode 1 and get the mean value of this image. And then basically, because they're stacking multiple images, so they could easily calculate the standard deviation of this mode 1. And one thing we can notice immediately right there is that the neural network, well, the DPI framework basically gives you a big uncertainties on the brightest part as well, right here, as you can see. But one thing they found also interesting is that if you divide your standard deviation by the mean value, the relative errors, they found that the relative errors are actually much bigger on the edge of the black hole image, which, yeah, they're not really sampling, and they're pretty confident about these part in this particular modes. So I think this is a really interesting sample that they showed using their DPI framework. So I'm not going to talk about these details. And one really interesting thing is that obviously most of the example they showed in the paper were simulated data. So the idea is that, can you apply this method to reconstruct the real data? And the answer seems to be yes. So I think what they did right here in this paper is that, so the Event Horizon Telescope data for M87 is now publicly available on GitHub. So what they did is that they throw their DPI framework, and using the observable from different days that are taken from the telescopes. And now they could generate a series of image and also their uncertainties using this DPI framework, which for me looks really interesting. So these are sort of the first validations on the real data. Yeah. Right. So in general, I think what this DPI framework is doing is that they basically gave us a really interesting examples on how you can combine variational methods with neural network and apply it on radio interferometry for image reconstructions. And it gives you it can sort of give you really quick estimation about like what are the possible modes and what are the uncertainties. And they also tested on the real data, so it seems to be working well for the black hole image. And so, and they also say that this is a generalized framework that could use for other image reconstruction in radio interferometry, which they shows a few samples in the paper, but I'm not going to talk about today. So right here, I think I'm ready to take questions, but I also like to bring out some of the thoughts or discussion that we could talk about later. So, so one thing I'm thinking about is that could this DPI framework be used more generally in radio interferometries, and also what kind of improvement could we do right here? And also, what I think one really key point right here is that for this to work, you really need to know your prior or your regularizers for each task, right? And also, also we could think about what's the difference between DPI or clean and their advantages. So with those, I think I'll stop here and ready to take questions.
Thanks, Joshua. This was really interesting. For the prior, they're using just a Gaussian prior, right? Like a multidimensional Gaussian prior.
So, so for most of the cases, yes. But for some of the for some of the image, they actually provide two different priors or two different regularizers. And I think in this case, they use something called maximum entropy and the TV2, which I have no idea what. Well, I have no detailed idea about what it is, but the only thing I know is that there were different priors used by different groups within EHT when they reconstruct the image a while ago. But yeah.
Okay. And they also have to give a form of the likelihood, right?
Yes.
Like specify.
Yes.
Okay.
So I think what they did right here is that they basically use a chi-square to
okay.
as a likelihood. Yeah. And I think one really interesting thing is that you need to have a forward model that brings your proposed image back into observable to compare with the and I think that's one of the key points. I feel like yeah, you need to have a really good forward model to do that. And different forward model might give you slightly different results.
One more clarification question. So why is like what's the dimension of why it's like 4 numbers?
What do you mean by 4 numbers?
Like, is it like the complex phase, the visibility, amplitude?
Yeah, right. Sorry. So I think in event horizon, so basically when the real observable only contains, so it's a bunch of visibilities which contains amplitude and phase. So basically it's like a complex number, a series of complex numbers. But I think
how big was it? How big was y?
How big? I think it's a vector that you can describe ranging from 100 data points to 1,000 or 10,000.
Okay.
So it's not too big.
But pretty big.
Well, I think it's Well, it's not that big as a neural network. But I think what they did right here is that I think they're using something called closure phase and closure amplitude. So when we talk about these amplitude, usually we only talk about their absolute value and their phase. But I think what Event Horizon Telescope found is that because they thought there might be a lot of errors directly taking out phase. So what they end up doing is that they take a 3-point correlation, 3-point function of a phase and do it in some subtracting way. So you can have a closure phase by taking the 3 visibility points and generate a series of data. So, and closure amplitude, it's I think it's a 4-point function apply on amplitude. So I think these two are really technical, and I only see them being used in the Event Horizon telescopes.
Right. So, like, can we think of the closure parameters as summary statistics of the whole visibility spectrum? Okay.
So, so I think one really interesting thing is that I can imagine if you choose a different likelihood function, you might end up having different posteriors right here.
Right.
And to choose this P Y of X, I honestly think there's a huge range of exploration used.
Yeah, it seems like the chi-square likelihood they have here like has covariances built in, but I mean, we don't know that it's Gaussian. The likelihood is Gaussian, right?
I doubt it's going to be a Gaussian in reality, but I don't know.
Mhm.
That's really, yeah.
So I think maybe one of the interesting connections with kind of what Maxime talked about before was, I mean, if you have in some sense, the difference between Y and X is just the effect of the detection apparatus. Is that right? Or is it also take into account like losses of photons when streaming through the universe and things like this?
Oh yeah, so the real Y actually, well, it's a real data, so it actually includes anything that could possibly happen from black hole till the observer. So interstellar electron could potentially change some of the properties of these observables. And if you one of your atomic clock or one of the one of your observable sites, whether it's really bad, that could also like change some of these quantities right here.
Do we have simulations of all the process of the photons? Like
I think there are some within the Event Horizon Telescope pipeline, but probably not in the publicly available pipeline, I guess.
The reason I ask is one could use the simulations to learn P of Y given X. And I think that's kind of what, you know, I don't know, maybe Maxime, maybe you can comment. I don't know if you find this to be, it's somewhat similar to the empirical Bayes work you were doing, but instead of posterior inference, they were doing kind of non-amortized posterior inference, and you were kind of working on prior learning with amortization. Is that a good connection?
Yeah, that's exact, yeah.
Yeah, that sounds like a really cool idea.
Well, I think in this sense, you can gain a lot of power by not amortizing things, by re-optimizing for every single image. It's slow, but you also get, I mean, you also can potentially, I mean, I don't know, there's probably benefits to both approaches in some sense.
Yeah, I think the really tricky thing is that you're not going to get many real observables in the future, right? Like this is only going to be applied on maybe 1 or 2 data in the futures. So
a few different images of different black holes, but
yeah.
So they can spend a lot of time in maximization for each image.
Yeah,
basically.
I think that's the spirit of what they are doing. Yeah, because we only have, well, M87 and maybe Sagittarius A stars in the foreseeable futures.
Yeah.
And for the observable, there's only few. Yeah. Now, one thing I found really interesting is that so when we talk about this observable, they are actually calibrated data. So one thing I've been thinking about is that we could also go back to the real raw data that you're actually measuring the voltage and all the crazy stuff directly from your telescopes and use the same framework. It might be more computational expensive, but I don't know. It sounds doable as well. Yeah. So I don't know how people are familiar with radio interferometries, but if some of you have tried, do you think there's a good framework for, I mean, radio interferometry in general?
Actually don't have good background in radio interferometry. What are some of the things that are considered when you generalize from one telescope to another?
Oh yeah, so I think this is a pretty general framework. I think there are lots of detail in different sites though. I think the basic concept is the same, that you're measuring visibility, that there are those data distributed sparsely in the first place. So I mean, for the case of, if you check into one of Yasher's and Phil's paper, then for SDP81, then I think you can see this part is being more broadly sampled for strong lensing, for examples. But I think the framework could still be the same. But I think different antennas might have different noise, so that's something we need to be careful when applied to different data set, I guess.
And can we rely on a high fidelity forward model too?
Oh, that's a really good question. I don't know. I trust EHT imaging, but for other part, I don't have that much of experience in their forward models.
I think if you want to learn a little bit more about related kinds of techniques, I think there's been some recent reviews on like deep image reconstruction for medical imaging, which is the effective problem is the same. It's kind of trying to get at the underlying image from observations. Though I know they may want to estimate some other properties of this, but that may be a place to see if I mean, if you're thinking about other applications, to see what kind of challenges these ideas have. I don't know if they did something, I mean, they may have different algorithms, but you may be able to see some of the related challenges in trying to do this, the reconstruction, like this map-based reconstruction with deep generative models.
Oh yeah, right. Like I remember like the fast MRI. It's actually pretty similar to radio interferometry, actually.
Mm-hmm.
So I think medical people are measuring things in visibility space as well. They do image reconstruction, then they do the treatment. I guess that's pretty cool. So I think this deep probabilistic imaging could also, I think in the paper they also say that this could be applied on any image reconstruction in general, not necessarily for radio interferometry. They just applied it on radio interferometry because, yeah, they work in this area. So
one of the big differences may be that if their likelihood is really just modeling the smearing of the photons by the, basically it's only basically modeling the point spread function of the camera,
mm-hmm.
and there's not a lot of other effects, then it may even be easier to do the medical imaging. Whereas here you've got the point spread function plus anything that happened between the stellar object or between the object in space and the photons arriving on Earth. If you want to model that, then it's that may be what makes this more challenging in terms of getting a high fidelity output posterior.
Right.
Also thought this was kind of the other way around from what we are generally looking for in strong lensing, because in strong lensing, the image is the observable. and we want to do posterior inference on Y. And for them, they have these samples of the image X, and they need to do some kind of dimensionality reduction to have an interpretation of what the whole posterior space is. Is that correct? Or can they, do they have a way of interpreting when they have some end samples of these images, what they want to get out of it?
I don't know that much of case for strong lensing in general, but the only few thing I know is Yasher's paper when for SDP81. I think there's only a long integral time of your observable. So, but I think what they end up doing is that they just directly analyze these observable instead of generating a bunch of image and estimate on top of it. That's what I remember.
For interferometry.
Yeah. So
imaging, right?
Yeah.
Okay, so I was thinking more of like when we have like visible optical band imaging.
Oh, yeah. Right. Yes. Yeah, for that part.
And like for us, Y would just be the lens model parameters, something we wanna infer for more downstream analyses. Are there other questions, comments? Okay, we are running past the hour, so thank you, Joshua. This was really interesting and I learned a lot. And let me know if any of you wants to present in 2 weeks.
Sounds good. Thank you, Chi.
Okay. Thank